Hey everyone, and welcome back. Ever just, stare at a piece of AI-generated art or read some text and think, how did it do that?
It's a great question because we're not just talking about AI that sorts your email or recommends movies anymore.
No, exactly. This is different. We're doing a deep dive today into generative AI, the kind of AI that actually, well, creates things, new things.
That's the key word, creates. We've looked at some really interesting material explaining how these systems work. They're not just recognizing patterns, they're learning the underlying rules of, say, images or music, and then generating something completely novel from that understanding.
Right. And it's definitely not just fancy copy pasting, which I think is a common misconception.
Oh, absolutely not. It's far more nuanced. The AI has to understand the deep structure, the grammar of an image, the harmony in music, the syntax of language.
And then it uses that understanding to build something fresh. It's a different beast entirely from discriminative AI, the kind that just classifies things like telling cats from dogs.
Precisely. That's prediction or classification. Generative is about, well, generation, creation.
So our mission for this deep dive is pretty clear. Let's get a solid foundation, really understand the basics of how this rapidly evolving tech actually functions.
Sounds good. A good starting point is probably the main types of models, the architectures they use. You generally hear about three big ones these days: GANs, VAEs, and transformers.
Okay, three main players. Let's start with GANs. Generative Adversarial Networks. The name alone sounds interesting. Adversarial.
Yeah, it really captures the core idea. Think of it like a contest or maybe a creative battle between two parts of the AI, two neural networks.
Okay, a battle. Between who?
You have one network called the generator. Its job is to create fake data, let's say, images of faces that look real.
Trying to make convincing fakes. Got it.
And then you have the second network, the discriminator. It acts like an art critic or a detective. Its job is to look at both real faces and the fake faces from the generator and decide which is which.
So one's forging, the other's trying to spot the forgery.
Exactly. And they both get better over time because of each other. The generator learns to make more convincing fakes to fool the discriminator.
And the discriminator gets better at spotting even tiny flaws in the fakes.
Precisely. This constant push and pull, this adversarial process, is what makes GANs so powerful for creating really realistic outputs.
But how do they actually learn? How does the feedback work? You mentioned a loss function in the source material.
Right. The loss function is crucial. You can think of it as a score that tells each network how well it's doing. For the generator, the loss is low if it successfully fools the discriminator.
And for the discriminator.
Its loss is low if it correctly identifies the real and fake images. So both networks are constantly trying to minimize their own loss.
And that minimization drives the improvement, this back and forth.
Yes, it's this iterative refinement. Create, critique, adjust, repeat. But it's worth noting, this constant battle can make GANs a bit temperamental.
Temperamental? How so?
Well, they can be notoriously difficult to train. Finding the right balance between the generator and discriminator is tricky. Sometimes they become unstable, or the generator might figure out one trick to fool the discriminator and just keep producing slight variations of the same thing.
That's called mode collapse, right? Where it gets stuck.
Exactly, mode collapse. It fails to capture the full diversity of the data it was trained on. So powerful, but challenging.
Okay, that makes sense for GANs. The adversarial approach. What about the second type, VAEs? Variational autoencoders. Sounds less confrontational.
It is a different philosophy. VAEs aren't about a battle. They're more focused on learning a compressed representation of the data, a summary almost.
A compressed version, like zipping a file.
Sort of, but more about capturing the essence. It learns something called a latent space. Imagine you want to describe the concept of chair without showing every single chair. You'd focus on the key features: legs, seat, back, maybe material.
The core properties that make a chair a chair.
Exactly. The latent space is like a mathematical map of those core properties. Each point in this map represents a slightly different combination of those essential features.
So it distills the data down to its fundamental characteristics.
Precisely. And the VAE has two parts: an encoder that takes the input data, like images of chairs, and maps it onto this compressed latent space,
Finding its coordinates on the chair map.
and a decoder that takes a point from that latent space map and reconstructs it back into a full chair image.
So to generate a new chair, it just picks a spot on the map.
Basically, yes. It samples a point from this learned latent space and runs it through the decoder. Because the latent space captures the underlying variations, the decoder can generate new, plausible chairs that it hasn't explicitly seen before.
That sounds smoother.
Yeah.
More stable than the GAN tug-of-war.
Generally, yes. VAEs are often easier to train and more stable. The trade-off, though, is that the generated samples might sometimes look a bit blurrier or less sharp compared to the best GAN outputs.
Okay, so GANs for maybe peak realism but tricky training. VAEs for more stability but potentially less sharp results. Got it.
That's a reasonable summary of the trade-offs.
Which brings us to the third major architecture, transformers. These seem to be everywhere now, especially with language models like ChatGPT.
Absolutely everywhere. Transformers have really revolutionized the field, particularly for anything involving sequences data where the order matters profoundly.
Like language, obviously. Words in a sentence.
Yes, but also music, which is a sequence of notes, or even generating computer code. Their big innovation is a mechanism called self-attention.
So attention. Okay, what does that let the AI do? It sounds like it's focusing on itself.
In a way, it allows the model, when it's processing one part of the sequence, like a word, to look at all the other parts of the sequence and weigh how relevant they are.
So it's not just looking at the immediately preceding word.
No, not at all. That was a major limitation of older models. Self-attention lets it look across the entire input, the whole sentence, the whole paragraph, and figure out the relationships between words, even if they're far apart.
So it can understand context much better, like understanding what it refers to in a long sentence.
Exactly that kind of thing. It understands pronoun references, complex grammatical structures, the overall theme. It weighs the importance of different input pieces to make a better prediction about the next piece in the sequence, whether that's the next word in a translation, a story, or a line of code.
That sounds incredibly powerful. No wonder they're so good at things like translation and writing.
Yeah, their ability to handle long-range dependencies in context is why they excel at those tasks, generating remarkably coherent and fluent output.
Okay, so we have these three key architectures, GANs, VAEs, transformers. But underpinning all of them is this learning process. You mentioned backpropagation earlier. How does that fit in?
Backpropagation is really the engine of learning for almost all modern deep learning, including these generative models. It's the algorithm the AI uses to adjust itself based on its mistakes.
Learning from mistakes.
Yeah.
We talked about the loss function measuring the error.
Right. So the model generates something, we calculate the loss, how far off it was from the target. Backpropagation is the mathematical process of taking that error signal and feeding it backwards through the network's layers.
Backwards.
Yes, from the output layer back towards the input layer. As it goes back, it calculates how much each connection, each knob or weight inside the network contributed to that final error.
Like figuring out which part of the recipe went wrong.
Kind of, yeah. It figures out which weights need to be nudged up or down slightly so that next time the output will be a little closer to the desired result, reducing the loss.
So it's this constant cycle.
Yeah.
Generate, measure error with the loss function, use backpropagation to figure out adjustments, make the adjustments, and repeat.
That's the core loop. Over thousands or millions of iterations, the model gradually tunes its internal parameters to get better and better at the generative task. It's like revising an essay based on feedback, but done mathematically at scale.
It's amazing to think about the journey to get here. Were there earlier attempts at generative AI before these complex models?
Oh, definitely. Early generative models were much, much simpler. Think about things like Markov chains.
Markov chains. Like predicting the next word based only on the previous one or two words.
Essentially, yes. They looked at probabilities. How likely is word B to follow word A? They could generate text, but it often didn't make much sense beyond a few words.
Right, because they couldn't grasp the bigger picture, the long-term context that transformers handle with self-attention.
Exactly. They lacked memory and a deep understanding of structure. The text could quickly devolve into nonsense because the model had no idea what it said 3 sentences ago.
So going from that to today's models that can write coherent stories or create photorealistic art, that's a huge jump.
It's a monumental leap, really, driven by algorithmic breakthroughs like GANs and transformers, but also massively enabled by increases in computing power and the availability of vast data sets for training.
Makes sense. You need the smart algorithms, the computational muscle, and the data to learn from.
The trifecta, really.
Okay, this has been super insightful. So to quickly recap the big takeaways from our deep dive today.
I'd say number 1, generative AI is about creating new content, not just analyzing existing stuff. It learns underlying patterns.
Right. And the main tools, the architectures, are GANs with their generator-discriminator battle,
The VAEs learning that compressed latent space, that essence of the data.
and transformers, which dominate sequential tasks using that powerful self-attention mechanism.
And the learning process itself relies heavily on backpropagation, using the loss function's feedback to iteratively adjust the model and get better.
It gives you a solid foundational picture. We didn't even get too deep into the weeds on limitations today, though.
No, that's a whole other deep dive. Things like bias in the training data showing up in the output, the huge computational cost.
Yeah, and the ethical stuff, copyright, deepfakes, authorship, important issues. Maybe for next time.
Definitely worth exploring further.
So we've got the fundamentals down. It's less magic, more complex process now.
Hopefully, yeah. Understanding the basics demystifies it a bit.
It does, and it leaves you with a kind of provocative thought, doesn't it? As these AI systems get better and better at tasks, we once considered uniquely human creativity, art, writing. What does that actually mean for us?
That's the billion-dollar question, isn't it? How does our role change in a world with increasingly creative machines?
Something to definitely keep thinking about. Thanks for breaking it all down.
My pleasure. Fascinating stuff.